Okay, hello everyone. So the last time we were going furthermore into the details about the zero order hold block, which is generating this staircase shaped curve for all of our signals. And this is what we're going to analyze today. Consider the following situation. We have a process plant with a transfer function GP of P. In our example, this is going to be an IT1 system, so stationary integrating system with first order delay. And now we try to consider the zero order hold block using the transfer function for the zero order hold block that we derived the last couple of weeks ago. So the transfer function for the zero order hold block was GO of P equal to 1 minus e to the power of minus pt over P, where P is the Laplace operator. Capital T is our sampling period, and e to the power of minus pt is actually the introduction of the dead time into the system. So we have 1 over P minus e to the power of minus pt over P as the transfer function x of P over R star, where x is the output of the zero order hold block, here x of t, and in the Z domain, or in the Laplace domain, first of all, we have x of P at this point here, and the input of the signal is R star, so R star of P in the Laplace domain. So the overall transfer function, as usual, is the product of both, which are implemented in the sequence here. So the overall transfer function is the transfer function of the dashed box around the two partial systems here, and the product is GO times GP. So if we have for the process plant, an integrating system with first order delay, the related transfer function would be 1 over P, which is the integrator, times 1 over P plus 1, so it's one pole at minus 1. So in the left half domain, it means that the system has a first order delay. So we multiply both transfer functions in order to get the overall transfer function. So what we get is this expression here, 1 minus e to the power of minus pt over p squared, because of this p and this is p squared combined, times p plus 1. And this is actually the output y over the input r star here. And now we learned that there are tables existing in order to do the transformation between the different domains. And now our goal is to get from the Laplace domain into the Z domain. So if we have a look at the table, the goal is to try to find the right row with the expression that we just derived in order to get to the Z domain and just look up the equivalent of the appropriate Z transport. The problem with those tables is always that there is just a limited number of expressions included in those tables. So we have to use a little bit more mathematics in order to work on this expression here in a way that we get, let's say, some simpler expressions that we will definitely find in the lookup table. So one thing is already here is e to the power of minus pt, which is actually, if we have a look at the grammar for the transformation, this is nothing but the consideration of a dead time of capital T. So this is actually simple, because we can just have a look at the first part, 1 over p squared times p plus 1. Try to solve that. And then we do the same, just one capital T dead time shifted to the future. So let's start with 1 over p squared times p plus 1. So if we would like to simplify that in a way that we can use the lookup table, what do you have in mind? Which mathematical tool could be used in order to simplify this expression furthermore? So what could be used? Any idea? Yeah.
Well, know it in German, Partialbruchzerlegung.
Yes, exactly.
Know it in
So the
English.
method of the partial fractions. So we can use this method in order to simplify this expression and calculate the sum of more simple terms, which is then the same as this 1 over p squared times p plus 1. So let's do that together to practice a little bit. Quickly open my Adobe annotator. Okay, so we have the function. We have the function. I want to write blue. Yeah, g of p equal to 1 over p squared times p plus 1. And we are looking for g of z. So in order to be able to work with the table, we are going to use the method of the partial fractions. Who is not familiar with the method of partial fractions? Okay, so everyone knows this mathematical method. That's good. So what is the approach? So how do we have to start now? So we say g of p is equal to what? What is the approach to get started here with partial fractions? Yeah.
I think we need to first identify the zeros of the denominator.
Yeah. Which are the zeros of the, so the poles of the function actually, yeah, which are
Zero, like 2 times 0 and minus 1.
correct. And what do we do with this information now?
We
So we divide this expression into actually into 3 parts.
so it would be now like the first denominator would be p plus 1.
This is my last one. Yeah,
And the others would be just p.
yeah. And which other one?
P squared.
P squared. P squared, exactly. So if you have a multiple pole, then you have to consider each of the multiples. So in our case, p and p squared. Okay, and then what is not known at this point are the coefficients, which we just call a, b, and c. And then in the end, this has to be equal to our original expression 1 over p squared plus times p plus 1. And now the goal is to calculate a, b, and c. And how do we do that? How do we find a, b, and c?
Can't plug in each one of the poles that will take one.
Yeah, so we are looking for a fast solution.
Yeah.
Yeah. So, I mean, we can bring everything back to the same denominator. So what do we have to do with the, so if we want to get back to the p squared times p plus 1 denominator, what do we have to do with a?
P plus 1.
We need factor p plus 1, exactly, and then what do we have to do with b?
P.
We need p times p plus 1, and then c times p squared. Okay. And now we can rearrange the numerator a little bit. Let's start with the highest exponent in p, which is p squared. So p squared, how often do we have p squared? Here we have a c times. That would be this. And here we have it b times. And b times p plus times p. So we have p squared times c plus b. And then the linear part, p, we have it a times. And here we have bp times 1, so plus b. And then finally the constant part is just a. So now we see that we have the same denominator, and we have a polynomial of second order in the numerator, which we know has to be equal to 1. So what are the 3 equations that we can derive from this situation now? Because we need 3 equations in order to find the 3 coefficients a, b, and c. So what about the p squared? Is it existing here in the original term? Yes or no? just see a 1, so there is no p squared. What does it mean for c plus b?
It's 0.
So c plus b has to be equal to 0, because p squared is not existing. So that's our equation number 1. What about the linear term, p? Is it existing here in the original term? No. So that means a plus b is also 0. And what remains is a has to be equal to 1. That's our equation number 3. And as we know a is equal to 1, we can immediately write down b is equal to minus a, which is minus 1. And then we finally have c equal to minus b, which is again plus 1. And in this way we have all the 3 coefficients, and we can write down our transfer function g of p as a over p squared, which is 1 over p squared, plus b over p, which is minus 1 over p, plus c over p plus 1, and c is 1, so 1 over p plus 1. And the good news is that the sum of individual terms is again the sum in each domain, in the time domain, in the p domain, and in the z domain. So we can now have a look at the table and try to find all of the individual terms here, and then we will finally have our g of z as the sum of the individual results here. So let's have a look at the table. So here in this table we have S as the Laplace operator, so this S is our P, it's the same. So we can use line number 3 and say 1 over S squared is in the Z domain Tz over Z minus 1 squared. Tz over Z minus 1 squared. So we have Tz over Z minus 1 squared. And then minus, the next one is 1 over P. So let's have a look for 1 over P, which is here in the table 1 over S. And in the Z domain for 1 over S, we get Z over Z minus 1. This one. Z over Z1 minus 1. Z over Z minus 1. And then plus. And now the last one missing is 1 over P plus 1. And 1 over P plus 1 is the same as line number 7. 1 over S plus A, where A is equal to 1. So we have Z over Z minus e to the power of minus AT. Z over Z minus e to the power of minus AT. Z over Z minus e to the power of minus AT, and A was 1. So minus e to the power of minus t. Okay, and that's already the result for g of z in the z domain. Any questions so far? So once again, what was the process to get from the Laplace domain to the z domain? We calculated the overall transfer function as a complex expression. Then we perform the method of partial fractions in order to have a sum of more simple terms here, and then we went to the lookup table and found the individual transformations, and then the sum of the terms in the Laplace domain is equal to this, well, it transforms to the sum of the individual terms in the Z domain. This way we found the Z transform for the transfer function. Any questions? Not the case. So then we can do a little bit of cosmetics here and write this in a different form. One thing is, so this was only our G star without this dead time. So our G of Z is actually this expression multiplied with 1, so we had it once, and then we have the dead time, and the dead time in the Z domain is a multiplication with Z to the power of -1, so one shift of one sampling period capital T into the future. So we have 1 minus Z to the power of -1 times this expression Tz over Z minus 1 squared minus Z over Z minus 1 plus Z over Z minus e to the power of minus t. And this is our G of Z. Okay, now if we say 1 minus Z to the power of minus 1 is actually the same as Z minus 1 over Z. So if we say Z to the power of minus 1 is 1 over Z, if we have the common denominator Z, then we can extend this to Z minus 1 over Z. And Z occurs here in every term, where we can cancel it, actually. Let's do it this way. Maybe in red. And the Z goes away. Then in the next step, we can find a common denominator here. So Z minus 1 squared and Z minus e to the power of minus t would be necessary for a common denominator. Z minus 1 squared and Z minus e to the power of minus t. And what we have here our Z minus 1. And now we need the individual factors for the parts in the numerators. So we need t times Z minus e to the power of minus t minus, and here we need z minus 1 times z minus e to the power of minus t. And for the last one, we need plus z minus 1 squared. This way. And then we can cancel z minus 1 with the square. And get close to the result. So now we can multiply out the denominator. Then we have a second order polynomial. Z times z is z squared. And then we have minus z times 1. Minus 1 times z is minus z. So we have added ones. And we have z times e to the power of minus t. The minus went out, so plus e to the power of minus t. And this is the linear term. And then the constant term is minus 1 times minus e to the power of minus t is plus e to the power of minus t. Okay, so that's the denominator. And for the numerator, let me quickly double check. No, this is correct. Perfect, so that's let's go in 2 steps. So we have z minus 1 squared, which is z squared minus 2z plus 1. That was this bracket. Then we have the middle term, which is z times z is z squared with a minus. Then we have minus z and minus z times e to the power of minus t. With this minus it's a plus. Z times 1 plus e to the power of minus t. And then we have minus 1 times minus e to the power of minus t is plus e to the power of minus t minus e to the power of minus t. Okay. And then we have plus t z minus t times e to the power of minus t. Okay. Now again, z squared minus z squared is cancelled out. And we get z squared minus z times 1 plus e to the power of minus t plus e to the power of minus t. This is unchanged. But then we have the linear part, z times. And here we have, let's use yellow. Here we, this one. So here here we have minus 2. Then we have 1 plus e to the power of minus t. And we have the t. Those 4. So, the t minus 2, and then the 1 plus e to the power of minus t. And then just the constant part remains, which is 1 is 1, and then minus e to the power of minus t, e to the power of minus t, which we have 1 times plus t times. Okay. And now we can go one step further and say we choose the sampling period to become t equal to 1 second. So every 1 second we have the values available. And then if we put that into the calculator, we get here 0.37 z plus 0.26 over z squared minus 1.37 plus 0.37. And that's our transfer function in the z domain.
Ja, das ist die 7 Sekunden.
Okay. Thank you. Okay. Any questions so far? Yeah.
Where did the expression 1 minus 1 over z came from? Like for the delay, it's
Which point?
it's at the very top. So to
At the
say.
very beginning.
Yeah.
Okay.
Before we did the cosmetic changes.
So this one.
This one, yeah.
Yeah. Okay. So let's have a look at the table. Another one. So here, if you have a look at the grammar of the table, then a shift with a plus here, if you have t plus t, would be a multiplication with z. If you go to the other side with minus t, then it would be a multiplication with z to the power of minus 1. So a shift to the right is a multiplication with z to the power of minus 1, and a shift to the left would be a multiplication with z. And now we had here in the transfer function we had 1 minus e to the power of minus pt, which is actually in the Laplace domain at that time. And at that time of just one sampling period, capital T. So in order to use this fact in our equation in the z domain, this multiplication with e to the power of minus pt would be a multiplication with d to the power of minus 1. So we have analyzed only the g star with just this part here, 1 over p squared over times p plus 1. But now we have to use the same again with the minus here. Just shift it one time step to the left. And this is actually then the multiplication with 1 minus z to the power of minus 1. Because the sum, independent of the sign, remains a sum also in all of the domains. So we calculated the result only for this 1 over p squared times p plus 1. And then we replaced the shift to the left, indicated here by e to the power of minus pt, with z to the power of minus 1. So, and this is what is written here. So this, maybe we can highlight it here. This is the shift of t to the future. So it's a dead time, capital T. And in the Laplace domain, this was the multiplication with e to the power of minus pt. This is the deadline. Okay, so what do we do with this result, with this Z transform? Let's have a look at the slides again. Okay. So, what you see here at the bottom right, in the bottom right corner of the slide, is actually the step response. The step response for our process plan. So if we apply a step here at x, then with such a stationary integrating system first order delay, we will get a step response that looks like that. So we have stationary, we see the integrating behavior. So if we do the excitation with a constant step, it remains constant forever, then the system reacts with a ramp at the output, because it's the integrated step. If you integrate a step, then you get a ramp. But it's a delayed ramp because of this pole here. So now that we have a discrete system now with a sampling period of 1 second, we have to be able to calculate the individual staircase steps now. And this can be done with our transfer function g of z. So here is the result that we just calculated. So this is for the sampling period t equal to 1 second. This is our z transform with these values here. If we would have chosen a different sampling period, for example, just 100 milliseconds or 10 milliseconds or whatever, then that would have led to completely different coefficients here in this term. So the sampling period is part of the coefficients here in your transfer function. That's what you have to keep in mind. So even if it is mixed up with other parameters, it is integral part of all these coefficients. However, now this is the expression we have to deal with, and now we can, for example, look for the impulse response of the system. On the other slide, we saw the step response. So how will the impulse response look like in a qualitative way? Could you describe this impulse response? So if this was the step response here, the delayed ramp, how would the impulse response look like?
Like a constant value.
Exactly, but how do we get there to the constant value?
Like we have a delay and then
Yeah, so we expect actually same the time constant as delay, and then go this way into the stationary constant value. Exactly. So let's calculate the quantitative exact timing behavior now using our result g of z. So if we consider the excitation to the system to be an impulse, then our r of z in the z domain would be just 1. So let's counter check that in the table. So here we have in the first row, we have the Dirac impulse, and the Laplace transform of the Dirac pulse is 1, and the Z transform is also 1. So that means if the excitation for the system is an impulse, then R of Z is equal to 1. And now the output Y can be calculated by the multiplication of G times R. Y is G times R, and if R is 1, then Y is exactly equal to G. So we can say now, if we go back to the script here, I add another page. Now we can say R of Z is equal to 1. We can say Y of Z is G of Z times R, which is just G of Z. And this is our 0.37 Z plus 0.26 over Z squared minus 1.37 Z plus 0.37. So now, with the excitation form impulse, we get this as a result at the output of the system. So that means we can now perform a polynomial division in order to calculate the individual values at the output of the sequence Y. So polynomial division. How does it work? So we can write down the numerator first, 0.37Z plus 0.26, and we divide that by the denominator, Z squared minus 1.37 0.37z plus 0.37. Okay, now we can start. How does the polynomial division work? What do we have to write down on the right side of this equation? What is our first term that we have to write down? Who can help me? Who's not familiar with the polynomial division? No? But it's actually like a normal division, so we look for the highest exponent here in this polynomial. So what is the factor that we have to multiply this first term with in order to get 0.37z? And that's 0.37 times z to the power of minus 1. So if we multiply now the whole bracket, the whole denominator, with this factor, then we get 0.37z. And then we have minus 1.37z times 0.37z to the power of minus 1. This is going to be a constant because z times z to the power of minus 1 is 1. So we have minus, and now I have to look it up. Where's my polynomial division?
0.51.
Sorry?
0.51.
0.51. And then the last one would be 0.37 squared. What's that? Zero point 0.14 times z to the power of minus 1. Okay, and now we have to subtract this, like in a normal division, from our original numerator. And we get here a 0, and then 0.26 minus 0.51. So that's a plus. So plus 0.77, and then minus 0.1 for z to the power of minus 1. And now we can do the same again. Now the next one would be, so the goal would be to eliminate this 0.77. That means we have to multiply with 0.77 times z to the power of minus 2. And again, the same game. Here we get then the 0.77. And then 0.77 times 1.37, what's that? Sorry?
0.77 times.
What's the product? 1.37 times 0.77?
1.05.
1.005. Let's say 1.
1.05.
005.
No, just 1 0. Just 1 0.
05. Okay. Yeah. So times z to the power of minus 1. And then the last one would be 0.37 times 0.77.
Point
0.28 times z to the power of minus 2. Okay. After subtraction, we get again a 0 here. And then we have 1.05 minus 0.14. That's plus 0.91 z to the power of minus 1, and then minus 0.28 times z to the power of minus 2. And now you see already that we can continue this forever. What we get is an infinite sequence of values, which is the impulse response of the system. Yeah. So this is what we see here on the slide again. Here we see the individual terms of our y of z. And now we can interpret this sequence of values, y of z, to the coefficients. These are the values at the time step that is indicated in the exponents of z. So you can think of the exponent as a position marker, and the values are the values at this time. So that's the multiplier of the capital sampling period t equal to 1 second that we decided to be 1 second here. So this is the value after 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. And you can continue this polynomial division forever, and then you get an infinite sequence of values, which is your step response. Okay? Any questions about that? So in the end, you calculate your z transform for your transfer function, and the same applies to your input signal. Your input signal is also a sequence of values. And then you multiply the transfer function with the input, which is your output in the z domain. And this expression, if you perform the polynomial division, then you get an infinite sum of terms where you can identify the coefficients as the values and the exponents as the multipliers of your sampling period capital T, which is in our case now 1 second. So we can try to reproduce that using MATLAB. So let's start the tool. Then you see how it works there.
This takes a while until it comes up. Did everyone install already the academic license of MATLAB and Simulink? If not, yeah, I would recommend to do it quickly, because a lot of examples will be done with MATLAB Simulink here. Okay, so let's start with the transfer function itself. So let's define our capital G of P being equal to TF. So TF is the command that you can use for the definition of the transfer function. And then with TF you need round brackets, and in the round brackets you need again these rectangular brackets. One pair for the numerator coefficient, and then separated by a comma, another pair for the denominator coefficients. And now that we have a function which is 1 over p squared times p plus 1, we have in the numerator just the 1. And then in the denominator we have p squared times p plus 1. So first we have to multiply out the bracket, then we have p to the power of 3 times 1. Then we have p squared times 1. We have no linear term in p, and we have no constant. So if I now hit return, then you see here the Laplace operator is s again, so our p, and we have exactly the function 1 over p squared times p plus 1. Okay, and with this function we can start now calculating the step response. So here MATLAB offers the step command to calculate the step response, and then we need to provide in round brackets, we need our transfer function that we just defined, our g, and then we can also define the time range that we would like to see in our figure. Let's say 10 seconds. Hit enter, and then the figure should come up here with the step response. So stationary, we have the ramp, and the curved part is the delay with which the system goes into the stationary ramp. But this is only the continuous representation. For us now, the discretization effect is of highest importance. So we can discretize this function now using the zero order fold block. So we can say actually this was our GP. So if we have a look at the slides again. So that was actually the GP of P, so I should call that actually GP. So GP is equal to G. the G is the discrete function. Here. And now if I add another comma and provide a sampling period of 1 second, then the command transfer function is automatically interpreted by MATLAB as a discrete transfer function with a sampling period 1 second. So I do that and hit return. Then I get something what I actually didn't want to get. So yeah, so that was not the right way. So we actually I should have put in the coefficients that we have calculated. So start from the scratch. So G is T equal to TF, and now we need to put in the coefficients for the numerator, which are 0.37 or 0.3678. So that's the first one, and then the second one is 0.2644. And that's it already for the numerator. And in the denominator we have 1 times c squared, and then minus 1.3678, 1.3678, and then 0.3678, 0.3678. And then we need another comma and have to provide the sampling period, which is 1. So now it's correct. And here we have our Z transform that we have just calculated before. So now I can say, so do we still have our figure? Yes, we do. And now I can say hold on, in order to make sure that with the next plot, the old one is not deleted. And if I now say step and provide in round brackets our new discrete transfer function, also for 10 seconds. Then mistake, I don't know why. Okay, now I found my mistake. So I made a mistake for the process plant. GP of P, so the transfer function of GP of P is just 1 over P times P plus 1. And I put in 1 over P squared times P plus 1. But this is the P which was coming from the 0 order whole block. So for the GP of P, I should have used only this one. So let's repeat that quickly again, and then it should be okay. So GP is equal to, how much time do we have left? No. Okay. Once again. Then the rectangular brackets. Ich habe mir mein MATLAB zugemacht, das gibt's doch gar nicht. How do I get that? No, it's all right. I just opened, somehow I just opened the second desktop, I think, and the other one disappeared. I don't know how to get back.
Windows R.
Windows R. Windows R.
Windows Tab.
Windows and Tab. Oh. Oh, okay. Perfect. Thank you. Okay. Thank you. So GP of P is 1 over, and now we have 1 times P squared plus P plus 0. TF, of course. So, okay, now it's the right function. And let's do the plot again. Step GP. GP for 10 seconds. Okay, looks like this, and now let's say hold on. To keep it and say step step G also for 10 seconds. Okay, this is what I wanted to see. Now you have the continuous case here, the delayed ramp in blue, and according to our calculated function g of z, we have that staircase curve, which is the result for the discrete system. This can be calculated by MATLAB in this way using the command transfer function. If you use transfer function without any sampling period, then it's considered to be a continuous transfer function. And if you provide separated by a comma behind the rectangular brackets a number, then this is interpreted as the sampling period. In our case, 1 second, so we have a step width for this staircase curve in 1 second. Now we can also calculate the impulse response. So for example, let's close this figure here and plot the impulse response using the command impulse G, also for, let's say, 10 seconds. Then it looks like this, as you predicted already. So stationary constant, but we have the delay going into this constant. And if we now have a look at the different steps here, then we will find that these are the coefficients of our Z transform, G of Z. So let's quickly counter check. So here we have the possibility to provide a data tip. And if I click to one step here, then see 0.368 is the first step. And that was exactly the result from our polynomial division. So z to the power of -1 means that it's already the value at 1 times capital T, so at 1 second. Then the next value was 0.77 after 2 seconds. So that was the second value that we calculated. So let's have a look at the second value and see it's 0.77 and so on. So using the polynomial division, we calculate this infinite sequence. So after a few steps, so for example after 10 seconds, we are already pretty close to 1. So it's never going to be really 1. There will be always a little difference to the 1. So the first few values would be sufficient in our case. Good. Any questions about that? So the important conclusion for today is that we can interpret
transfer function here in a way that we just multiply it with the input, in our case an impulse, can be anything, but in our case it's just an impulse, and then we have the output of the system, and the output of the system as a, is an infinite sequence of values where the height of the step is determined by the coefficient, and the exponent in Z determines at which position this value is going to be applied. Any more questions? If this is not the case, then thank you very much for today, and see you next week.